Okay, in this video, we're going to continue studying Markov decision processes. There's a very important equation called the Bellman equation, which is going to characterize what we call the value of a state of a Markov decision process, where the value of a state roughly means it's a measure of how much the agent would like to end up in that state. It's a measure of like how much payoff can they possibly extract from starting in that state. The Bellman equation is going to indirectly characterize the optimal policy by directly characterizing this thing called the value function. The Bellman equation is a form of a one-shot deviation principle, namely that to be an optimal policy, it's going to be enough to make a maximizing choice at every stage. So we don't have to think about deviations in all stages simultaneously, which would be a significantly more complicated optimization problem. And something slightly magical happens because a Markov decision process is somehow self-similar. This is a result of the Markov property that basically all stages kind of look the same because we don't remember anything from the past. It's going to turn out that all stages actually share exactly the same optimality condition. So what this means is that the optimization problem facing the agent who controls the MDP starts out looking extremely complicated and intractable, ends up being something that can actually be efficiently solved in practice. Now, the Bellman equation is an example of a thing called a functional equation. That is to say, an equation in which the unknown is a function rather than just a number. And it's going to characterize, so its solution is going to be what we call the optimal value function. The optimal value function is a thing that says how much payoff can we get for each state by following the optimal policy. Okay, so for every policy, so here I'm fixing to deterministic policies, so it's a function from states to actions. Every one of these has an associated thing called a value function, which I call V sub sigma, which is a function from states to real numbers. This is going to tell us the total expected payoff that we get from executing the Markov chain to infinity while following the policy sigma. So its definition is given an initial state Q, it's the expectation of this infinite discounted sum where the UIs are the payoffs that, of course, stochastically, and then we take an expectation, are resulting from following this policy sigma starting from the state where the initial state is Q. So this definition is somewhat difficult to work with, but then the idea is that the Bellman equation is going to simplify this. It's going to equivalently characterize V in terms of something that's a bit simpler. So let's think about the robot control example from the previous video. Here's what it looks like. Think about the policy to work in the high battery state and recharge in the low battery state. It just so happens that this is the optimal policy, although we don't have the tools to know this yet, but it happens that this is the optimal policy. So if we fix this policy, what we get is not an MDP, but an ordinary Markov chain together with a payoff on every edge. So that is to say, if we're in the high state, then with probability 1/2, we stay in the same state and we get a payoff of 1. With probability 1/2, we transition to the low state, get a probability of 1/2. And then in the low state, with probability 1, we transition back to the high state and get a payoff of 0. So what happens is I've focused on the arrows in the full characterization of the MDP. I've deleted all the ones that don't come from following the optimal policy. So that is to say, we never recharge in the high state and we never work in the low state. If you've worked with Markov chains before, you'll be able to see that we can write down some recurrence equations which are satisfied by the value function of this thing. So the easy one to see is that the value of being in the low state is equal to the value of being in the high state times beta. because we know that with probability 1, we're going to transition here, we get a payoff of 0 for that, but we accumulate an extra copy of the discount factor, and then we run from here, and we know that running from here will give us the total payoff VH. And then the value of being in the high state is, well, so we know that whatever we do, we're going to get a probability of 1, and then we're also going to either land in the high state or we're going to land in the low state. So we get, and we're taking an expectation, so we get half of the value of the high state plus half of the value of the low state, but each with a copy of, each with an extra copy of beta. So this is the recurrence equation, which is satisfied by these two things. And we can solve this just by pure algebra. I haven't actually written down the solution because it's a little bit tedious, but you can see we can substitute this for VL in this equation, and that's going to give us, after rearranging a bit, this is going to form a quadratic equation in VH, which we can just solve. So that's the way that you can calculate the value function of a policy just by kind of pure algebra. Okay, now we're going to have a very important reindexing trick. We last saw this for we last saw the reindexing trick for repeated games when we were calculating the payoff that resulted for playing some finite state strategies in something like the iterated prisoner's dilemma. This is an extremely similar thing. It's basically the same method, essentially. Because a repeated game after we fixed finite state strategies really starts to look a lot like a Markov chain, although there's no probability there, but it's a very similar idea. Essentially, we've just added probability at this point. If you think about it, the value of being in the current state is equal to the sum of the payoff that we get right now plus the total payoff from all future stages. And the total payoff from all future stages is given by the value function, because the value function tells us what's the total payoff from starting in that state. So it's like starting in this state is like getting some payoff now and then restarting in the next state. Except that we get one extra copy of the discount factor. So the second time is given by the total payoff of the next state multiplied by one copy of the discount factor beta. So what that is to say is that this thing, the value function of our policy, which is defined to be this thing, where the UIs are the payoffs that we get from following the policy, is going to be equivalently given by U0, which is the payoff that we stochastically get from following the policy, plus beta times this thing, and after reindexing, this turns out to be exactly V sigma of Q1. And what I've forgotten to write here is the conditional part, that this is the U0 and the Q1 given the initial state Q0 and the action sigma of Q0. So specifically going from here to here to here, this is exactly the reindexing trick for geometric series. This is the same thing that we use to calculate the same kind of values for repeated games like iterated prisoner's dilemma. Okay, now at this point we are basically arrived at the Bellman equation. So everything we've done up to now works for any arbitrary policy, but suppose we want to talk about the optimal policy specifically rather than just any old policy. So the optimal policy is the one that maximizes this total expected discounted payoff. So by a form of the one-shot deviation principle, we know that the payoff that we get now, U0, is going to be the largest. So sorry, U0 plus the discounted value of the next state is going to be the largest thing that we can obtain for any action. So what that means is that the value function of the optimal policy, which is called the optimal value function, is going to satisfy this equation here, that it is the maximum over all actions we could choose of the payoff that we get plus the value of the next state, given the current state and the actions. We're maximizing over this action. So remember that there's a conditional probability that's defining the Markov decision process, which is the joint probability of U0 and Q1 given Q0 and A. So all we're doing is we're applying V to Q1 and then taking an expectation. So this equation here, this is called the Bellman equation. And the solution of the Bellman equation, so here V is the unknown thing here. So the V that satisfies this equation, because it appears on both sides, is the optimal value function. So it satisfies this definition. It is the value function for the optimal policy. So where sigma is the policy that will maximize the discounted sum. So this is noticeably very closely related to subgame perfect equilibrium. So what we're doing is we're checking one deviations in every state of the Markov chain.